All right, let's go through paper 4, which is a theory extended paper for chemistry. That's for IGCSE from Cambridge International Examinations, CIE. And that's October, November, the winter 2018, variant 1, so 0620/41. All right, let's begin.
Great, let's get started.
Question 1. The following formula represent different substances. We have Al for aluminium, Ag for silver, CaCO3 for calcium carbonate, CH4 for methane, Cl2 for chlorine, Cu for copper, and SO2 for sulfur dioxide. All right, answer the following questions using only these substances. Each substance may be used once, more than once, or not at all. State which substance is used to make food containers. Okay, we use aluminium for that. Okay, B is added to a blast furnace to remove impurities during the production of iron. Okay, that is calcium carbonate, CaCO3. C, the main constituent of natural gas, that is methane, CH4. D, a cause of acid rain, and that is sulfur dioxide, SO2. E, a gas which bleaches damp litmus paper, and that is chlorine gas, Cl2. And F, a gas which contributes to climate change, that is also methane, so CH4. All right. Question 2. The table gives some information about 4 different particles, A, B, C, and D. All right. Question part A is complete the table. The first row has been done for you. So, number of electrons. We need to find the number of electrons in B. Well, we have the number of protons here, and the charge is 0, which means that there's exactly the same number of electrons as there is protons. Okay, C, it's the same thing. The charge here is 0, so that means that there has to be the same number of protons as there are electrons. Okay, here, there's a different number of protons to electrons. There's one more electron. Electrons are negative. So that means the charge is -1. And now we look at the electronic structure. Well, you don't even really need to calculate it because C already has 18 electrons and D has exactly the same number of electrons, so it has to have the same structure. 2, 8, 8. 2 in the first shell, 8 in the second shell, and 8 in the third shell, just like C. Okay, good. B. You have 2 particles from the table which are isotopes of each other. And remember, isotopes have different number of neutrons. They have the same number of protons, but different number of neutrons. So we look at this and say, oh, these 2 have exactly the same number of protons, but their number of neutrons are different. So that means 2 particles, that would be A and B. There we go. C, element Z is in the same group of the periodic table as A and is less reactive than A. State the identity of element Z. Okay, first of all, we have to look at where element A is. Okay, element A has 11 protons. So let's look at, and also if you look at the electronic structure, 2, 8, 1, that means there's only 1 electron in the outer shell. It should be in the first group. Okay, so we're looking in the first group, and because that's where we're expecting it to be, and it has 11 protons. So the small number is the proton number or the atomic number, and the large number is the mass number. So we're looking for the number with 11. That looks like sodium to me. And if we go down the groups on this side, it becomes more reactive, and on this side it's less reactive. Okay, so that means that element Z is either lithium or hydrogen, but we're assuming they're talking about just a little bit less reactive, so let's say it's lithium. Okay, so the element Z, that is lithium. Okay, you can either write Li or the whole word lithium. It doesn't matter, both are right. Okay, D. C is unreactive. Use information from the table to explain why. Okay, let's look at C. Okay, C. It's unreactive. Oh, let's look at this. This is why it's unreactive. Okay, 288. It has a full outer shell. So is D. Okay, but D is an ion. It's charged. All right, so that's why it's unreactive. So C has a full 8 electrons in the outer shell. All right, let's move on to question 3. 3A. Copper 2 nitrate decomposes when heated. 2 gases, oxygen and nitrogen dioxide, and a solid are made in the reaction. A sample of copper 2 nitrate was decomposed using the apparatus shown. Okay, so it was heated over here. Copper 2 nitrate was heated. Then the gases came up, because that's often what gases do, and they were forced down through the sodium hydroxide. And then they bubbled up through the sodium hydroxide. Any reactions that would happen with the sodium hydroxide would occur, and anything left behind would be pushed up through this arm. All right, down through the water, and then whatever remaining gases there are collected as X, and this volume would increase over time. All right, so let's look to see what it says. 1. Complete the chemical equation for the reaction. Okay, so first of all, we have 2 copper nitrate produces oxygen plus a certain number of nitrogen dioxide and then something else. Okay, let's look at the ends. We have 4 ends, so 2 from the nitrate and 2 because there's 2 moles of it. So that is, there's 4 ends, so there should be 4 there. Now, let's add up how many, what's left. So right now we have 2 coppers needed. So for the oxygens, we have 4 times 2, that's 8 oxygens, plus another 2, that's 10. So we have oxygen, we have 10 on that side, and on this side, we have 3 times 2, that's 6, and 6 times 2 is 12. So we have 12 oxygens. So we're missing 2 oxygens and 2 coppers. Okay. All right, so what can we create with this? What we can create with this is 2CuO, 2 copper oxides. All right, so that is the formula. 2. Only oxygen gas is collected at X. Explain why. All right, so copper oxide, well, that's a solid. So that's not going to be a gas pushed through these arms. Okay, the other 2 gases, we have nitrogen dioxide and oxygen. Now, nitrogen dioxide is acidic. And acidic bubbled through aqueous sodium hydroxide. Sodium hydroxide is alkali. It reacts, and that becomes a neutralization reaction. And the only one that doesn't react is oxygen. So the oxygen is what's collected. Okay, so the nitrogen dioxide is acidic, so it reacts with the sodium hydroxide. Because it reacts with sodium hydroxide, it's not there to collect at X. All right, moving on. B. Nitrogen dioxide and other oxides of nitrogen are formed in car engines. Explain how nitrogen dioxide is formed in car engines. So the reason why nitrogen dioxide could be formed in car engines is because there's a lot of nitrogen and oxygen in the environment, in the air that comes in to the engine. And the engine is very, very hot, and this hot condition causes the nitrogen and oxygen to react and creates nitrogen dioxide. Okay, so nitrogen and oxygen from the air react at high temperatures in the engine, because nitrogen doesn't react on its own. It needs something like a high temperature. Nitrogen is very unreactive. And now for some calculations. C. A teacher heated 18.8 grams of copper 2 nitrate. 1. Calculate the number of moles of copper 2 nitrate present in the 18.8 grams. Okay, so the formula for calculating moles, we have moles equals mass over relative molecular mass. Okay, now we have, that is 18.8 grams divided by, now copper 2 nitrate. That's CuNO3 2. Okay, so we have to find the mass. Okay, so we need to find the mass of copper, nitrogen, and oxygen. Okay, so the mass of copper is 63.5. The mass of nitrogen is 14, and the mass of oxygen is 16. So we have, that's 1 copper, so that's 63.5, plus, how many nitrogens do we have? We have 2 nitrogens. That's 2 times 14 for nitrogen, plus we have 6 oxygens. 3 times 2 is 6. 6 oxygens. So that's 6 times 16 oxygens. And if we calculate that out, we get 187.5 grams per mole. But that's 4 significant figures. That's a bit excessive. So we should probably say 188 grams per mole. Okay, so we say 188 because we have 3 significant figures here. We should probably have 3 significant figures here, grams per mole. And if we do that calculation, we get 0.1 moles. But if you look at this, we have 3 significant figures, so we should probably have 3 here. So 0.100 moles. 0.100. At this level, they probably won't take off the marks for not adding the other 2 zeros, but it's a very good practice to get into because at A level, they absolutely will. Okay, or IB or AP or any of those, they absolutely will. Okay, 2. Calculate the maximum number of moles of oxygen that can be made by heating 18.8 grams of copper 2 nitrate. All right, so to do that, we need to look at the formula again. We need to look at the ratio. So if we look at the ratio of CuNO3 to O2, you'll see that CuNO3 to O2, that's a 2 to 1 ratio, equals 2 to 1. Okay, so it means for every oxygen you need 2 copper nitrates, but you have the copper nitrates, you're trying to figure out the number of moles of oxygen, so for every copper nitrate you need half an oxygen. Okay, so that is 0.100 moles of copper nitrate times 0.5 equals 0.005 moles. Okay, so the answer is 0.005. Okay, and remember that's just because we have a 2 to 1 ratio. You know how many moles of copper nitrate you have. You need to find the number of moles of oxygen, so you have half the number of moles of oxygen. All right. 3. Calculate the maximum volume of oxygen at room temperature and pressure in centimeters cubed. Always look at this. That can be made by heating 18.8 grams of copper 2 nitrate. All right. Okay, this is a gas equation. So we say the volume at room temperature and pressure equals the number of moles times 24 decimeters cubed per mole. That's a molar gas volume. Decimeters cubed. They want the answer in centimeters cubed. Okay, that's very, very important. Or else you'll get it wrong, obviously. Okay, so that is 0.005 moles times 24 decimeters cubed per mole gives you 1.2 decimeters cubed. Now you need to convert that to centimeters cubed, which you could do in this original equation. That's okay as well. You multiply by 1,000. So that equals 1,200 centimeters cubed. So be very careful of whether it's in centimeters cubed or decimeters cubed, because when you're talking about molar gas volumes, you're talking about decimeters cubed. D. A sample of copper 2 nitrate was dissolved in water to form an aqueous solution. The aqueous solution was split into 3 portions. A separate test was done on each portion as shown. Okay, so test 1, aqueous sodium hydroxide was added, and a light blue precipitate formed. Step 2, test 2, zinc powder was added, and the solution changed from blue to colorless, and a brown solid formed. Test 3, we don't know what the reagent was. Well, we'll figure it out soon, I'm sure. And ammonia gas was produced. So give the formula of the light blue precipitate formed in test 1. All right, so what we have is we have copper 2 nitrate, CuNO3 2. We add sodium hydroxide, NaOH. So basically, the OH and the NO3 swap. And that gives us CuOH2, copper hydroxide. All right. 2. Explain the changes seen in test 2. Okay, so test 2, we had the copper nitrate and zinc powder was added to it. And the solution changed from blue to colorless and a brown solid formed. Okay, and the reason why this happened is because zinc is more reactive than copper, and so there was a displacement reaction. The zinc displaced the copper. Okay, so the zinc is more reactive than copper, and a displacement reaction occurred, so zinc displaced the copper. So when this displacement reaction occurred, the brown solid, that is the copper. The copper came out of solution and became a solid. So a brown copper solid formed, and the process of forming that brown copper solid took the copper ions out of solution. Okay, and that copper ions in solution are blue. But zinc ions in solution, they're colorless. Okay, so you can say the zinc nitrate is colorless, or the blue copper 2+ ions are removed from the solution. They're the same mark, really. You're pretty much saying the same thing, and that's the reason why it turns from blue to colorless. All right, so that's 4 points for 3 marks. That gives you a little bit of wiggle room. 3. Identify 2 reagents that must be added to the aqueous copper 2 nitrate in test 3. So test 3, we had 2 reagents added and ammonia gas was produced. Well, the ammonia gas was produced because of the nitrate. Okay, so the test to test for ammonia gas, it's pretty much the same thing. You're saying what is the test for ammonia gas? The test for ammonia gas is sodium hydroxide, or NaOH, plus aluminium. Okay, so remember, just because this isn't the practical or the alternative to the practical exam, you still need to know the different tests. So you need to know them for everything. E. Copper 2 nitrate can be made by reacting copper 2 carbonate with nitric acid. One of the products is carbon dioxide. Write a chemical equation for the reaction of copper 2 carbonate with nitric acid. Okay, so first of all, copper 2 carbonate. CuCO3, that's copper 2 carbonate. Okay, because the carbonate has a 2 minus, copper 2 plus. Okay, and so plus nitric acid, HNO3. I'm leaving a blank here so we can figure out the stoichiometry of the equation in a moment. Okay, and that produces, okay, so basically they swap, sort of. Okay, so we produce, and that produces CuNO3 2, copper nitrate. All right. And because remember, nitrate has a charge of -1, so you need 2 of them. Plus CO2, because it said carbon dioxide was produced. And what we have left over, we have some hydrogens, which are not taken account of here. And, well, when we do the balancing, we'll see that there's extra oxygens. It's also adding water. All right, so if you look at this nitrogen, there's 2 of them. Whenever I try and balance these, I always look at the ones that shall only come up once. So copper and nitrogen. Copper, there's 1 here, 1 here. That sounds good. Carbon, 1 here, 1 here. That sounds good. But nitrogen, there's 1 here and 2 here, which means we'll probably need 2 there. Okay, so now we have 2H. H is there, and we have 2 H's here. So far that's good. And now, the final one, we just figure out if we have the same number of oxygens. On this side, we have 3 oxygens plus 6 oxygens So that's 9 oxygens. Over here we have 3 times 2, that's 6 oxygens, plus 2, 8, plus 1 is 9. So that should be balanced. And it includes the reactants that we were told are there. It includes the carbon dioxide. And everything should work out. So that is the answer. Okay, 2. Carbon dioxide is added to the air by living things. Name the chemical process by which living things add carbon dioxide to the air, and that is respiration. Okay, and 3. Carbon dioxide is removed from the air by plants. Name the chemical process by which plants remove carbon dioxide from the air. Well, the opposite reaction to respiration is photosynthesis. All right. 4a, sulfuric acid is made industrially by a 4-step process. Step 1, sulfur is burned in air to produce sulfur dioxide. So the sulfur reacts with oxygen to produce sulfur dioxide. Step 2, sulfur dioxide is converted into sulfur trioxide. So obviously it reacts with more oxygen. Step 3, sulfur trioxide is reacted with concentrated sulfuric acid to produce oleum. And oleum is reacted with water to produce concentrated sulfuric acid. All right. 1. Some sulfur is obtained by mining, and name one other major source of sulfur. Okay, one other major source, fossil fuels. Okay. 2. What is the name of the process by which sulfuric acid is made industrially? And that is called the contact process. Okay. 3. Describe the conversion of sulfur dioxide into sulfur trioxide in step 2. And your answer should include a chemical reaction for the equation and the essential reaction conditions. Okay, let's start with the essential reaction conditions. Okay, so first of all, we need a catalyst. So vanadium pentoxide, B2O5, is a catalyst. And it occurs at 1 to 5 atmospheres. So it occurs at a pressure of between 1 and 5 atmospheres. Okay, the temperature needs to be pretty high. A temperature of 450 degrees Celsius is required. And finally, let's put in the chemical equation. Okay, so for this, we have 2SO2, because we have to convert sulfur dioxide into sulfur trioxide. We have to react it with oxygen, plus O2. Okay, and this is a reversible reaction. Okay, so that produces 2SO3. Okay, we have 2 S's, 2 sulfurs. We have 4 oxygens plus 2 oxygens, 6 oxygens on the left-hand side, and 2 times 3, that's 6 oxygens on the left-hand side. So it all balances well. So remember, this symbol is important. It means it's an equilibrium reaction, so it's reversible. Okay. And you might look at it and say there's only 4 points here, but one of the marks was for saying it's a reversible reaction. You could either write down it's a reversible reaction, an equilibrium reaction, or you could just write in this symbol here. Okay? Both are okay. So that makes it 5 marks. B. When concentrated sulfuric acid is added to glucose, C6H12O6, a black solid is produced. The concentrated sulfuric acid acts as a dehydrating agent. So that is a hint. What is removed from the glucose in this reaction? Well, when you dehydrate something, you're removing the water. So they're kind of giving it to you there. It's water is removed. And name the black solid produced in this reaction? Well, it's carbon. And carbon, there is a lot of carbon in C6H12O6. So that makes sense. C. The gas hydrogen sulfide, H2S, is produced when concentrated sulfuric acid is added to solid potassium iodide. The reaction involves oxidation. Define the term oxidation in terms of electron transfer. Okay, so whenever you're looking at define the term oxidation, sometimes I say it in terms of oxygen. Is it gain or loss of oxygen? Sometimes it's in terms of electron transfer. Okay, so oxidation is loss of electrons. I always remember the old saying, this is what my teacher taught me when I was in high school. Leo, the lion, says grr. Loss of electrons is oxidation, gain of electrons is reduction. That's the way that I always remember it. Okay, and then you can't mistake it. If it wasn't in terms of electron transfer, oxidation would be the gain of oxygen. But both of them, you have to know both definitions and read the question carefully about what they're actually asking for. 2. Complete the dot and cross diagram to show the electron arrangement in a molecule of hydrogen sulfide. Show outer shell electrons only. Well, we know that hydrogen only has one electron. So that's one electron for hydrogen. I'm just going to use the dot for hydrogen. Doesn't matter if you use the dot or the cross for which one, as long as you're consistent. Okay, for every unpaired electron, you have to pair it. Okay, so sulfur needs to have an electron with it for every hydrogen. Okay, and now sulfur needs 8 electrons in its outer shell. 2 of those electrons are from hydrogen, so it has 6 in total, specifically from sulfur. So that means we could put 2 up here and 2 down here. You want to make sure they're paired, and you want to make sure that they're not right next door. They're about as far away from all the other pairs as you can get them. All right, good. 3. Hydrogen sulfide has a simple molecular structure. Explain why hydrogen sulfide has a low boiling point. Okay, the reason why it has a low boiling point is because the attractive forces between the molecules are weak, so they need very little energy to overcome them. Okay, so the attractive forces between molecules are weak, so need little energy to overcome. Okay, the forces between molecules, you can also call that the intermolecular forces. Don't call them the intramolecular forces because those are within the molecule, and those it would be better to call them the covalent bonds, because that's what the intramolecular forces are. Okay, so you can say the intermolecular forces are weak, or you can say the attractive forces between molecules. Both are fine. D. Dilute sulfuric acid reacts with aqueous sodium hydrogen carbonate in a neutralization reaction. So we have sulfuric acid, sodium hydrogen carbonate produces sodium sulfate and water and carbon dioxide. Okay, so in a titration, 0.200 moles per decimeter cubed of aqueous sodium hydrogen carbonate was used to neutralize 20.0 centimeters cubed of dilute sulfuric acid of concentration 0.150 moles per decimeters cubed. Now, if you look at this, there is a trick. You have to read the question carefully. I know you don't have much time, but look at this. It says moles per decimeter cubed, and then it's to neutralize 20.0 centimeters cubed. And here again, it's decimeters cubed. That means you have to be very careful when you're doing your calculations that you convert to the correct units. You need to be working with the same volume, whether it's centimeters cubed or decimeters cubed. You need to be working to the same. Okay, so 1, calculate the number of moles of dilute sulfuric acid used in the titration. So the calculation for moles, that's moles equals concentration times volume. Okay, and the volume is in decimeters cubed. Okay, that is very important when you're talking about moles. It's decimeters cubed. It's just the way that we do it, just for consistency. Okay, so the concentration was 0.150 moles per decimeter cubed times a volume of 20.0 centimeters cubed. You have to divide it by 1,000. And then you're working with decimeters cubed rather than centimeters cubed. Okay, so the answer there is 0.003 moles. So you write down 0.003. All right. Okay, very important you look at the units. Calculate the number of moles of sodium hydrogen carbonate needed to neutralize the dilute sulfuric acid. Okay, so if we look at the mole ratio between sodium hydrogen carbonate and dilute sulfuric acid, we have H2SO4 to NaHCO3. So H2SO4 to NaHCO3, we have a 1 to 2 ratio, 2 to 1 ratio. So H2SO4 to NaHCO3 is 1 to 2 ratio. So that's a equals 1 to 2. Okay, so we just calculated the number of moles of dilute sulfuric acid, and that was 0.003. So 0.003 moles of dilute sulfuric acid. We need 2 times the amount of NaHCO3, so that is times 2 is 0.006 moles. 0.006 moles. All right. And 3, calculate the volume in centimeters cubed of 0.200 moles per decimeters cubed of aqueous sodium hydrogen carbonate to neutralize the dilute sulfuric acid. Now this exam is really testing your knowledge of converting between centimeters cubed and decimeters cubed. Okay, there's a lot of marks hanging on whether you can do this conversion, so make sure you know that. So the formula to use is moles equals concentration times volume, and you're looking for volume. So volume equals moles divided by concentration. Okay, so that is, you just calculated that at 0.006 moles divided by, you're told that it's 0.200 moles per decimeter cubed. Okay, and that gives you 0.03 decimeters cubed. Okay, but they want the answer in centimeters cubed, so you have to multiply that by 1,000 equals 30 centimeters cubed. Okay, so you need 30 centimeters cubed of the sodium hydrogen carbonate to neutralize the dilute sulfuric acid. And that's the end of that question. Question 5. Hydrogen gas reacts with iodine gas. The equation is shown. So 2 gases produce a gas. Okay, the reaction is reversible and can reach equilibrium. What is meant by the term equilibrium? Okay, so equilibrium means that there's a reaction happening forward and there's a reaction happening backwards. But the rates of reaction for the forward reaction and the backward reaction are equal. So the forward and backward reactions occur at equal rates, so the concentration of substances remains constant. Now the important word there is rates. Okay, it's the forward reaction is occurring and the backward reaction is occurring. It's not just that the substances remain constant. It doesn't look like any reaction is happening, but both reactions are actually happening at the same time, so that everything looks like it's staying still, but it's not. B. The graphs show how pressure affects the yield of hydrogen iodide, Hi, at 2 different temperatures. All right, so explain why the yield at 500 degrees Celsius does not change as the pressure is increased. All right, so the reason why is because there's the same number of moles on either side. Okay, so the same number of moles on either side. So remember, when you're looking at gases, if the reaction just has gases, that's 1 mole here. It's 1 mole here and 1 mole here. So that's on this side there's 2 moles, and on this side there's 2 moles. If the number of moles are the same on either side, then changing the pressure does not change how much is produced. 2. What can you conclude from the difference in the yield of hydrogen iodide at the 2 temperatures shown? Explain your answer. Okay, so what you can conclude with this is that the forward reaction is actually exothermic, because when it's at a higher temperature, there is a lower yield. So the forward reaction is exothermic, so there's a lower yield at higher temperatures. If it was endothermic, it would have a higher yield at higher temperatures. All right. C. The graph shows how the concentration of hydrogen iodide, Hi, changes after hydrogen gas and iodine gas are mixed together in a sealed container. So, when is the rate of reaction fastest? Okay, it doesn't have exact time, so you just say beginning, middle, or end. Okay, the fastest rate is at the beginning. Then it slows down, and at the end it's stopped. Okay, so at the beginning. Okay, 2. The reaction was repeated at the same temperature and pressure, but in the presence of a catalyst. Draw a graph on the same axis to show how the concentration of hydrogen iodide changes with time in the presence of a catalyst. And remember, a catalyst just speeds up the rate of reaction, but doesn't change anything. It doesn't get used up. It doesn't change anything. So you have the same amount of stuff that you start with and end with. Temperature and pressure is the same, so it has to finish off at exactly the same level. But it goes faster at the beginning. Okay, so that is, well, probably draw it all the way along. Might want to do this a bit more carefully. Probably use a pencil. That's with a catalyst. All right. Good. D. A mixture of hydrogen gas and iodine gas is allowed to reach equilibrium. 1. Increasing the pressure of a gas increases its concentration. State and explain the effect of increasing the pressure on the rate of the forward reaction. So when you increase the pressure, does the rate increase or decrease, and why is what it's asking. Okay? So first of all, the rate of the forward reaction is faster because the pressure is increased, so that means there's more collisions per second. So the rate of the forward reaction is faster with increased pressure as there are more collisions per second. So the next one, 2, state and explain the effect of increasing the temperature on the rate of the reverse reaction. Does the rate increase or decrease, and why? So again, the rate of the reverse reaction is increased as the particles have more energy. Because of that, they have more collisions that are successful, more successful collisions. So the rate of the reverse reaction is faster as particles have more energy, so there are more successful collisions. Okay, now both of these questions are asking about the rate of the reaction, not about the yield. Remember, it's an equilibrium reaction and gases, so increasing the pressure doesn't change the yield of either of them, but the rates of the forward and the backward reaction are increased. Okay, we're talking about the rates of the reaction, not how much we get from it. 6a. Ethane, C2H6, is a member of the homologous series called alkanes. Ethanol, C2H5OH, is a member of the homologous series called alcohols. Alkanes are hydrocarbons. What is meant by the term hydrocarbon? Okay, a hydrocarbon is a compound that only contains carbon and hydrogen. Okay, so a compound that only contains carbon and hydrogen. So there's 4 key words in that. First of all, it's a compound, not an element. Okay. It only contains carbon and hydrogen, not anything else. That's a word that is often left out. And carbon and hydrogen, hydrocarbon, very important. So those are 4 key things that you need to remember. 2. All members of a homologous series can be represented by a general formula. State the general formula of alkanes. Okay, the general formula for alkanes is CnH2n plus 2. Because remember, here's an alkane, C, these are all H's. Okay, so there's 2 H's for every carbon along the chain, and then there's 1 at each end. Okay, so the general formula for alcohols is, there's 2 options. You can say CnH2n plus 1 OH. Okay, you have to make sure that the 1 is still small, a subscript rather than large. Or you can say CnH2n plus 2 O. Okay, so both of those are okay. And the reason why, remember, for alcohols, here's an example of an alcohol, CCOH, HH. We have, for every carbon, we have 2 hydrogens. We have 1 hydrogen at one end, and we have an OH at the other end, or wherever it happens to be. All right. State 2 characteristics other than having the same general formula of members of a homologous series. Okay, so members of a homologous series have similar chemical properties. So you get the same sort of chemical reactions occurring. Okay, they also have the same functional groups. So all alcohols have the OH. Okay. Other things you could put down is you could say that they all have a gradual change in physical properties. They also, another thing you could put down is that the neighboring members differ by, the only difference is a CH2. There's a CH2 added to the next one along the list. B, ethane can react with chlorine in a substitution reaction. State one essential reaction condition. Okay, the essential reaction condition for this reaction that we're talking about, ethane and chlorine substitution reaction, that's UV light or sunlight. 2. Draw the structure of the organic product formed by substitution of one of the hydrogen atoms in ethane with chlorine. Show all of the atoms and all of the bonds. Okay, so we're looking for ethane. So I always say monkeys eat peeled bananas. Monkeys eat peeled bananas. Ethane has 2 carbons. Okay, so we have C, C. Okay, it says one of the hydrogens was replaced with chlorine. So it doesn't matter which one you put it on, I'm going to put it there. Then all the other spots, so that there's 4 in total, have hydrogens. It says to show all of the bonds, and that's all of the bonds. And name the product of the substitution reaction between ethane and chlorine that does not contain carbon. All right. So if we look at that, we start off with ethane, and we add Cl2. Okay, just drawing it out here. So basically these two swap places. Okay, and what you have at the end is this molecule that we already drew and HCl. Okay, now there's no water involved in this reaction. So this is not hydrochloric acid. Hydrochloric acid needs to react with water to become hydrochloric acid. This is called hydrogen chloride. And this is a gas. Okay, so if you wrote hydrochloric acid, it would actually be wrong, even though it's HCl. C, propan 1-ol is an alcohol. The structure of propan 1-ol is shown. Propan 1-ol reacts with ethanoic acid to form an ester. Give the name of the ester in this reaction. So we take the alcohol first, so that's propyl, and then we take the acid, ethanoate. Okay, propyl ethanoate. At D, ester Y has a structure shown. Okay, give the molecular formula of ester Y. Okay, the molecular formula is just showing what is on here. Okay, so we have carbons. We have 1, 2, 3, 4, 5. We have hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And oxygens, we have 1, 2. C5H10O2. 2. Draw the structures of the carboxylic acid and the alcohol used to make ester Y. Show all of the atoms and all of the bonds. Give the name of the carboxylic acid and the alcohol. Okay, so if you look at this, the reaction occurred basically along here. And on one side, we have the alcohol. So that would be an OH. I'm just going to cross out that. And here, we have our acid, OH. All right, so that's basically how it works. So the acid, let's look at that one first. We have our C, double bond O. We have H. It says show all of the bonds, so I'm going to say O to H. So show the OH bonds. It does say show all the bonds. Okay, and this is called, there's only one carbon, so monkeys eat peeled bananas. One carbon, starts with M. That's methanoic acid. Okay, and the structure of the alcohol, that is, we have 1, 2, 3, and then another carbon up here. And we have an OH, and all the other ones have H's. And we have to draw on all these H's. Can't just draw the lines to show that there'd be an H there. All right, so this, it has 4 carbons. Monkeys eat peeled bananas. 4 carbons, starts with B. So it's butane, and we start, and to find out which one the alcohol's on, we look at the one that's closest to the end. So 1, 2, butane, 2, all, because it's the alcohol, OH. Okay. Okay, and finally, we're on page 14. This would be on the very, very back of your exam, a 3-mark question that apparently a lot of people forgot to look at. So always look to make sure there's no question on the very last page. Okay. E. Nylon is a polyamide. Complete the diagram to show the structure of nylon. Show all of the atoms and all of the bonds present in the linkages. Okay, so remember, to create nylon, you need a dicarboxylic acid, okay, and that is, we're going to do that with the colored in square. We have our colored in square. We have on each side, we have a COOH, COOH, okay, plus a diamine, which we'll do that with that square, the hollow square, and that's NH2, NH2. Okay, so if you notice on the square, so basically we should have a C, N, N, C, C, N, N. Okay. On the C's, we should have a double bond O, double bond O, double bond O. On the N's, we should have an H. Okay. Okay, and it just keeps going. All right, and that is it. That is the end of this exam. I hope you have found this useful. If you did, I'd really appreciate a thumbs up, and we really like it when you subscribe. And if you have any questions or comments, please put them in the discussion section below and we'll answer as soon as we can. All right, and have a great day.